Hello, this video is going to be showing you how to solve exponential and logarithmic equation, and those two being inverse of each other, we're going to use one to solve an equation that includes the other. Okay, just like when we do multiplication and division, you know, one unders the other. When we solve equations, that's the idea. All right, so first of all, let's first use our calculator to find some of those values. So I have my calculator here, and I hope you can see that screen. Yeah, I think you can. And I'm going to type in 5, and this here is an exponent, so 5 caret key for the exponent, and then log base 5, so on my calculator that would be this one, log base 5, and then inside the log my argument is a 3. And if we remember that an exponential function, that's an exponent to that base 5, and a logarithm base 5, those two are inverse operation of each other, so we expect them to cancel each other out and to end up with just a 3. So we're going to confirm that with the calculator, and indeed this is a 3, right? So this would be equal to 3. So look at this one here. 2 to the power of, and the power is a log base 2. Well, those two being inverse of each other, they will cancel each other out, and then we'll just be left with a 9. So let's confirm on the calculator. 2 exponent, and then I need a log base 2 of 9. And sure enough, I get a 9. So you kind of get the idea, I hope. This is the other way around. So here I had the 5 to a power of a log base 5. Now I'm going to have a log base 4 of 4 to a power. And if you remember your power rule, this says that we could take this exponent and bring it to the front as a coefficient. So that would give me 7 times log base 4 of 4. And a log base 4 of 4 says 4 to what power gives me 4? Well, 4 to what power gives me 4? When those two values are the same, that will become a 1. So this here is just going to be equal to 7 times 1, which is just going to be a 7. Same here, log base 5 of 5 to a power. This power is going to be brought, let's change color so we see it better maybe. This exponent here can be brought to the front as a coefficient, so I'll have a 3/2 times, and then my log base 5 of 5. A log base 5 of 5 says 5 to what power gives me 5? Well, that's just a 1, so that will be my 3/2 times a 1, which is just going to be 3/2. Okay? So on this one, it's a natural log e cubed. And now remember, the base we don't see here for a natural log is a base e, right? So we have e to what power gives me e cubed? Well, that's going to have to be 3, right? Same here, the base I don't see is a base e, so e to what power gives me e to the 0.005? Well, that's going to be 0.005. And you're going to say, well, why are we doing that? We're doing that because in a little bit when we're going to solve equation, those are the steps we're going to have to add to undo something, okay? So that's what we're practicing here to realize this is true. E to the power of a natural log, those two being inverse of each other, I'm going to end up with just a 4, and here same, I'm going to end up with just 5 over 4. All right. Inverse property of, now I'm not quite sure that's a real name, but Mr. Record here, because I'm using the notes from Mr. Record, just has that here. I think he made that one up. I'm not quite sure. Inverse property of logarithmitating. Inverse property of logarithmitating. I'm not sure this is a real board right there. An exponential. So this just says that log base b of b to the n is just going to be n. log base e of e to the n, well, that's just going to be n. So what does this property say? It says that when I have a base that is the same as the argument, remember this is the argument, this here can be brought to the outside, right? So I'm going to actually redo that here. So that log base b of b to the n can be rewritten. We can take that n power here to the front as a coefficient, so that will be n times, and then I have a log base b of b. When you have the same base as the argument, that's just always going to be a 1, because it's b to what power gives me b, that's going to be 1. So this ends up being n times 1, which is just n. And this was the same thing here, right? So in words, how would we write that? When the base and the argument, and when I mean the argument, I don't mean the argument including the exponent, right? I mean when we have taken that to the outside as a coefficient, when that's done, when the base and the argument are the same at this point, then when the base and the argument are the same or are equal, how am I going to write that? We're going to end up with just the exponent that we used to have. As in log base b of b, and we're going to say this is equal 1. Now this one is a real word. Now this one I know for sure that's a true word. This one we're good here. Exponentiating means when you take both sides of an equal sign and you're raising both sides to an exponent. You're exponentiating the expression. So this is an exponentiation of log base b of a. So we say b to the power of log base b of a, and we say those two are inverse operations, so we just end up with the argument there on an a. And same thing here, e and the natural log of e of a, sorry, the natural log and the e are inverse operation, we end up with just an a. Okay? So, and it's the same thing when your exponent when the exponent is a logarithm, with the same base as the exponent had, right? Then we are left with just the argument. So just what was inside, right? Because everything else cancelled. Okay. So let's look at a few here. We're going to use those properties of exponential and logarithmic expression to simplify. So no calculator, right? We're practicing those properties. So if I have a natural log of e to the 3x, well, remember, what's the base that I don't see here? The base I don't see is the base e. And we just said that when those two are equal, they're inverse operation of each other. So that will be the same thing as bring that 3x to the front. As a coefficient, and then natural log of e that goes to a 1, and so that's just going to be equal to 3x. So here, let's write that first as an exponent, right? So a cube root is the same thing as a power of 1 over 3. So here we have a natural log of e to the second power, and then that cube root here just becomes over 3 here. Those two are inverse operation of each other, so they're going to cancel each other out. The exponent is going to come to the front as a coefficient, so we're going to write 2/3 natural log of e. That natural log of e goes to 1, and therefore the answer is just going to be 2/3. Here we're exponentiating, so we have a 10 to the power of 2 log x. Remember, this, when we don't see a base, that's a common logarithm with base 10. So base 10, they're going to be the same. But here we are going to go reverse. We're going to actually bring that 2 inside as an exponent. So that's 10 to the log of x squared, and now those two just go to 1, and so therefore we're going to be left with just x squared. Same here, we're going to take that 2, we're going to bring it to the inside to square the argument, and that will be e to the natural log of x plus 1 quantity squared. Those two are inverse of each other, they cancel each other out, so we're left with just x plus 1 quantity squared. Okay. And now we're going to keep doing a little bit of the same thing here, just to keep practicing. Those two are inverse of each other, so that will just result in x plus 2. Those two are inverse of each other, but we have to be very careful here, because there is no parentheses. So you see how we're trying to make you see that those two look alike, but they're not. Here, the 2 is part of the argument of the natural log. Here, it's part of the argument, it's inside parentheses. This 2 is not part of the argument. For these 2, I'm going to apply the laws of exponent that says that when I add exponent, I used to have the same base that I multiplied. Okay? When you add the exponent, it used to be the same base that used to be multiplied. So what does that do? Well, the natural log and the e here are going to go to 1, so I'm left with just an x here, and here I have an e squared. And we normally write the number in front of the variable, so that will be e squared x. So notice how those are completely different answers, right? So be careful. Is the 2 in the argument or is it not? It's going to decide what you need to be doing. So let's look at that here. Same kind of deal. We have an exponent here that's 2 plus a natural log base 5. It's an addition, so I can separate my exponent with 2 bases of 5. So 5 squared times 5 log base 5 of x. Again, when you multiply the same bases, you would add their exponents. That's what's happened here, right? Those are added. So undoing that would give us back to here. And then we have a 5 squared, which is 25. 5 and a log base 5, those are inverse of each other. They cancel each other out, and we are left with just that x. So 25x is what we will have. Now, here I'm adding 2 logs, but they are not common base, right? Normally the property says that when you have common base, so like if I had a log 10 3 to the x plus a log e cubed, that would be a common log, that would be a common log, then I can just multiply their insides, right? But this is not the case here. This is a common logarithm. This is a natural logarithm. Those are two different bases, so I cannot do anything here. So that's going to stay the way it is. So this one we cannot simplify. Oh, I mean, we cannot put them together, combine them, but now I can simplify individually. So forget about this natural log for a minute and let's just look here. This is a base 10 that I don't see, and when the base and the argument are the same, they go to 1, right? So take your 3x to the front, and then I have a log base 10 of 10, and that will go to a 1, and so I'm left with just 3x. So that's for that portion. Now let's focus on this portion here. A natural log has a base e, and when the base and the argument are the same, they go to 1. So bring this 3 to the front. This now goes to a 1, and we are just left with the 3. So this will be my answer, 3x plus 3. Okay, we're going to solve this equation, and here it's putting in words. Oops. Something, I don't know if you see that on my screen. There we go. I hope that didn't bug you, but something just popped up on my computer screen here. Okay, here we go. We're going to solve this equation. Now, before I can do anything with that 2 to a power, that exponential expression here, I need to get rid of that 3, right? Because that 3 is not part of anything. It's not in a log, and it's not in the exponent either. So I'm going to subtract 3 from both sides, just like you did in algebra 1, and then you're left with 2 to this 3 minus 2x equals an 11 minus 3, well, that will be 8, right? Now, at this point, you have options. You could use a natural log, a log base 2 on both sides. Or you can say, I know what 8 is. 8 is 2 cubed, right? And now I have a base 2 and a base 2. So I can say, therefore, those exponents are equal. 3 minus 2x equals 3, right? I have a base 2 and a base 2, so those exponents have to be equal because that's equal right there. So you can put them equal to each other and then just solve for x. So we're going to subtract 3, so I have a negative 2x equals 0, and then x equals 0. Now you want to check your answer, right? So if you plug in a 0 here, 2 times 0 is 0, 3 minus 0 is 3, 2 cubed is 8, and 8 plus 3 is 11. So that checks, right? So check. Okay, let's do this one. There is no plus or minus here, so I do not have to add or subtract something first. So I can, oh, but I have a times 3, so I can actually divide by 3, right? Because that's a multiplication there. Okay, so I have e to the 2x plus 1 is equal to 12 divided by 3, that's a 4. At this point, we can take a natural logarithm on both sides. Why a natural log? Because this is a base e, so the natural log is what I want. So I need a natural log of e to the 2x plus 1, and then a natural log of 4. Whatever we do on one side of the equation, we have to do on the other, right? So we need to take a natural log on both sides. This here is just a number, right? There is no variable left, just a number, and if we put that in our calculator, we will get actually a value. Here, the natural log and the e, those are inverse of each other, so they cancel each other out. So I'll have a 2x plus 1 left over, natural log of 4. And now let's get x by itself, so subtract a 1. Notice how I do not put that in parentheses because the 1 is not part of my argument, and if I want to be very clear, I would write it like that. That would make it very clear that this negative 1 here is not part of my argument. And then divide by 2. So I'm going to write that up here. So we have x equals the natural log of 4 minus 1, everything divided by 2. So the natural log of 4 minus 1, all of that divided by 2. And, okay, I was reading my directions here. So we're going to round our answer, so that means I'm going to put that in my calculator. So if I put this in my calculator, I need a fraction to start with. Then I have a natural log of 4. Make sure you get out of the argument, right? And then minus 1, and then divide all of that by 2. And the answer will be, and we're going to keep 3 digits after the decimal. So we're going to round to the nearest thousand, and so it's 0.193. Okay, so x, this is the exact answer here. That's the exact answer. And then about 0.193. That's an approximate answer. Okay. Let's look at this and see what we need to do. So first of all, I have a plus 4 here by itself, no logarithm, no exponential there, just that plus 4. So I'm going to do that first. Minus 4 on both sides. So now I have 2 to the 3 minus x is equal to 10 minus 4, which is 6. At this point, I need to get this exponent out of there. So to do that, I need to take a log, right? That's how we solve for exponent, logarithms. So I'm going to take a base 2 because that's what I have here. So I want a log base 2 of 2 to the 3 minus x. And then whatever I do on the left, I have to do on the right. So log base 2 of 6. And again, this might look strange, but this is just a number. There is no variable left here. So that's just a number. I put it in my calculator. It will give me a value. So here I have a log base 2 of 2. Those two are inverse of each other. They cancel. The 3 minus x will be brought to the front as a coefficient. So we have 3 minus x. That's a 1. And then a log base 2 of 6. And to get x by itself now, we're going to subtract 3. And I put that in parentheses to really identify that my minus 3 is not part of my argument. And then I still have a negative here, so I need to divide by a negative 1 everywhere. So x is equal to negative. And when you divide that whole thing here by negative 1, that becomes negative, and that changes to a plus, right? So we have minus log base 2 of 6, and then plus 3. That will be my answer, my exact answer for the x. And then I plug this in my calculator to find the approximation. So I have a negative log base 2 of 6, get out of the argument, and then plus 3. And so again, remember to get out of the argument here before you do the plus 3, right? And then the answer will be about 0. So x is about 0.415. Okay, what's left for us to do? Let's see. We're already 23 minutes into the video, so okay, I'm going to leave this one alone here because it's similar to the one we just did. We're going to have to subtract 1 first, then divide by 3, and then take a natural log on both sides. Okay, so I'm going to leave this one alone. We already did something similar. I'm going to look at this one. Okay, I have an exponent, but I have one on either side. So I need to take a log, but what base? Well, I'm looking at 2 and at 8, and I'm answering myself. I'm asking myself, which one could I rewrite in terms of the other? Well, we know that 8 is the same thing as 2 cubed, right? So I'm going to rewrite that 8 as a 2 cubed, and then to the x minus 1. By doing that, and I'm going to go ahead now and distribute this 3 to my exponent here. So I have a 2 to the 3x minus 3 is equal to 2 to the 3x plus 4. And by doing that now, I have a base 2 equal to a base 2. So therefore, their exponent have to be equal to each other. So I have 3x minus 3 equals 3x plus 4. And now I'm just going to solve for x here. Oh, notice what happens here. Unless I messed up. And I do not think I did, actually. This one is an interesting one. So when you're subtracting 3x from both sides, I'm going to write it down so you can really see it. See how those are gone? And what we have left over will be a negative 3 equals 4. No more variable, but look at your statement. Is that a true statement? Is negative 3 equal to negative 4? No. When that's the case, that means no solution. When you end up with something that's not true. Of course, you need to do what I just did, right? You go back for just a few seconds and check that you didn't mess up anywhere on your math when you work it out. But then if you realize you didn't, then this would not be a mathematical true statement, so no solution. Okay, let's try this one. This one is a little scarier, maybe, but yes, this one is definitely scarier. So let's wait on this one. Let's go here. I have a base 2 and a base 5. Those are not going to match or give me the same base, and there is no way I can rewrite one in respect to the other. So I'm going to use either a natural logarithm on both sides or a common logarithm on both sides. Doesn't really matter. So I'm going to do a common logarithm. So log of 2 to the x plus 2 is going to be equal to a log base 10, right? Common logarithm of 5 to the x minus 3. So notice the only thing I did is I took a log, common log on both sides, and that's legal if I do it on both sides, right? Then I'm going to take my exponents and I'm going to bring them to the front as coefficients. So then I have x plus 2 times log of 2 is equal to x minus 3 times log of 5. Now remember, log of 2 and log of 5, those are just numbers. There is no variable left in there. So the only variable we have left here will be this one and this one. So what I'm going to do is... oh, well, I don't really have an option, do I? I'm going to subtract it from both sides. I'm going to take that whole term and subtract it. So I'm going to end up with x plus 2 log of 2 and then minus that whole thing because I'm subtracting it from both sides. And then that will be equal to 0 because there will be nothing left on that side. At this point, well, I'm going deeper and deeper and deeper. I don't know if I wanted to go that deep into that. Okay, I'm going to finish it, but I don't know I wanted to do that. So I'm going to distribute this log here, and I'm going to distribute this one. So x times log, right, of 2, and then the log of 2 and the 2, so plus 2 log of 2. Do the same with this one, distribute the log 5 here. So we have minus x log 5, and then negative 3 log 5, but a negative negative becomes positive, so plus 3 log 5. And that's still all equal to 0. Okay, now anything that has an x, I'm going to keep on that side of the equal. Everything that doesn't have an x, meaning those two right there, I'm going to subtract them to bring them to the other side of the equal. So I have x log 2, and then keep this one with an x in it, so minus x log 5 equals, this one doesn't have an x, so I'm going to subtract it to the other side. And this one doesn't have an x, so I'm going to also subtract it to the other side. Okay, that is just a number, no more variables, so I put that in my calculator and it's going to give me an approximated decimal. For those two, however, I have an x and an x, so I'm going to factor out an x. And here I can just leave that the way it is, or I could actually go ahead and put that in my calculator and get a decimal. Let's just leave it for now. And now I need that x completely alone, because remember we're solving for x, right? We want to know what x is. So I'm going to divide both sides by that. So x equals, so we had this one up here. So that's a negative 2 log of 2 minus 3 log of 5. And all of that is divided by this here, because I'm going to break it apart from the x and do that multiplication by division. So log of 2 minus log of 5. Now that looks very, very nasty and scary, but this is actually our answer. And we would put that in our calculator and get a decimal, but for the sake of time for the video here, because we're already in 30 minutes, I'm not going to do that. All right. I want to do a little bit, so those were exponential equations that we solved. Let's look at what happens when we start with a logarithmic equation. So when I start with a log, the first thing I'm going to look is where do I have my x's. So I have one here and I have one here. So when you add two logs, what can you do to their inside? Remember the property? When we add two logs, what do we do to their inside? We multiply, right? So that would be an x plus 2 times x, and that will be the argument of that natural log, and then that's equal to a natural log of 8. This side, I don't have to worry. This is not a variable. I don't have to solve for anything. It's already a number, right? Natural log of 8 is just a number. I have a natural log of something equal to a natural log of something. So we're going to exponentiate base e on both sides. See how I took a base e on both sides? That means that those two are going to cancel each other out, and I'm left with just x plus 2 times x is equal to, those two are going to cancel out, and we just have an 8. And now it's just a simple equation, right? So we're going to distribute this x squared plus 2x, subtract the 8, make it equal to 0, and now see if you can factor that. So x, and what can I multiply to give me a negative 8, but add up to give me a 2? That will be a negative 4 and a positive 2. Actually, no, I want a 2 when I add, so the largest number has to be positive, and this one negative. So let's check. Multiply negative 2 and 4 will give me my negative 8, and add them will give me my positive 2. So I know those are right. Okay, when I multiply two things and I get a 0, I know that either x plus 4 equals 0, in which case x equals negative 4, or x minus 2 equals 0, in which case x equals 2. Now when we're solving equation, and I didn't do it anymore after a while up there, but it's critical, especially when we start with natural logarithms, or any logarithm really, is that we check the solutions. So if I plug in a negative 4, is that possible? Remember, we cannot have a 0, so you might want to put that somewhere. No 0 and no negative number in argument of the log, right? In an argument of the log. So we cannot have 0 and no negative number inside the log. So if I plug in a negative 4 here, negative 4 plus 2 will give me a negative 2. That will give me a negative number inside the log as the argument. We cannot have that. So I don't even need to check the other ones. This one's out. Not a solution. Let's check 2. 2 plus 2 is 4, so that will be working here. 2 is still just positive here, so this is actually my only solution. And sometimes it's going to happen that you have none of them, right? You come up with 2 solutions, but when you check them, none of them works. And that is sometimes the case. Okay, I'm going to do one more, and then I'll call it a day here. Okay, let's pick. Alright, so this one is similar to the one we just did, right? Because here we had 2 logs added, so we took their insides and we multiplied their insides. Here we have 2 logs, we subtract, so we're going to take their inside and we're going to divide their inside, okay? So we're going to have a log base 2 of x plus 2 divided by x minus 1, right? Because this one is the minus, and then all of that has to be equal to 3. Now switch to exponential. Remember we said the base to that power is equal to that. So 2 to that power is equal to x plus 2 over x minus 1. 2 to the third power is 8. And at this point, we just need to solve that rational. So this, we multiply both sides by x minus 1. And we distribute this 8. So I have 8x minus 8 is equal to x plus 2. And I'm going to subtract x from both sides. So minus x minus x. And I'm going to add 8 to both sides. So 8 minus x is 7x equals to 10, and then divide by 7. And remember we said we have to check our solutions, right? So once we have the solution, we're going to see if we plug it in, do we get a negative or a 0. So 10 over 7 plus 2, well, both of those are positive and I'm adding, so that's not going to give me a negative. 10 over 7 minus 1, well, that would give me a 3 over 7, which is still positive, so we're still okay. So this one works. Okay, I think that's plenty long here for solving equations. So I'll see you in class next time.